and so differentiate 1 with respect to, say for example, let us say we want to eliminate I, you differentiate 1 with respect to space, and therefore you have dou square V x of t by dou x square equals minus L dou square I t dou t dou x, and similarly you differentiate the second one with respect to time, right, and therefore dou square I x comma t dou x dou t equals minus c dou square V x comma t divided by dou t square, all right, and so what does this mean? We get dou square V by dou x square must be L times C times dou square I dou square straightforward substitution. I mean, let us quickly make sure that we have the stuff is dimensionally consistent, right. Sanity check. What are the units on the left hand side? Volt square per meter square. On the right hand side, what are the units of this guy here? Remember, L in this notation is inductance per unit length. I mean, you have to bear that in mind. I mean, it's a little bit of notational abuse, right? In a book, you would have some, nicely drawn calligraphic symbol for L, right? I can't do that, unfortunately, so I will just call it L. So LC is basically has got dimensions of time square per meter square, and the time square in the numerator and the time square in the denominator cancel, and therefore we are all a happy family. Does that make sense, folks? Very good. So, all right. So this, by the way, as you all know, is called the wave equation. All right, and the question is, how on earth do we solve this thing now? Right? And fortunately, it turns out that there is a smart guy who figured this out. Right? By this name, D'Alembert, solution to the wave equation, and he just discovered that any function of the form f of x minus, this is supposed to be c, all right. This c is not to be confused with the c of the LC, right. As you can see, we are running out of letters here, and so this is f of x minus ct. He claims that any function of this form, right, or f1 of x minus ct satisfies the wave equation, and well, who are we to argue with a great man? We just basically substitute this in the equation and check if it works or not, right? Oh well, what is the partial derivative with respect to x? The second derivative with respect to x, it's simply f1 double prime of x minus ct, where this prime refers to the derivative with respect to the to the argument, correct, by just using chain rule, alright. So, dou square V by dou x square is this, dou square V by dou t square is going to be, c square times f1 double prime of x minus ct, alright. And so, if you want to make these two equal, what do we do? We want to make LC times the derivative with respect to the second derivative with respect to time, which is this guy here, to be equal to the second derivative with respect to space, all right. So, stare at this and tell me what do we see? Well, that is true if the c square is equal to 1 over L times c, and c is basically, or rather this calligraphic c is has got dimensions of, c equals plus minus 1 over square root LC, alright, and this basically has dimensions of velocity, right. That makes sense. I mean, c times t must have dimensions of distance, it is consistent with the fact that x minus ct must have dimensions of distance. Is that clear? So, therefore, the solution to the wave equation is, you can write this as v of x comma t can be written as some function f1 times x minus ct, right, where c is plus minus 1 over square root LC. So, if we deliberately say c is 1 by square root LC, then you can think of the solution as f1 of x minus ct plus some other function f2 of x plus ct, and why we justified in adding another function? It is a linear differential equation. If f1 of x minus ct is a solution and f2 of x plus ct is a solution, then any linear combination of the two solutions will also be a solution, right. If you are not convinced, you can go and do the, you can plop this into the wave equation and see that it satisfies, right. So, c is basically 1 over square root LC, which is basically the velocity of light. All right. Now, well, that is the voltage. What comment can we make about the current? We go back to our, once we know the voltage, we go back to this thing here. So, let us say the voltage f1 of x minus ct, what is the derivative with respect to x? This is simply f1 prime of x minus ct, correct, and this must be minus L times the partial derivative of I with respect to time. So, what comment can we make about I of x comma t? 1 over L times C times f1 of x minus c. Does it make sense? Now, this 1 by L, again I would like to warn you that this C is not the capacitance, it is the velocity of light. And before we get confused any further, let us replace C with the formula that we already derived. What is C in terms of L and C? Is 1 by square root of, which is therefore 1 by square root of L by C. Okay. So, this is F1 of x minus divided by square root of L by C. What are the dimensions of square root L by C? Impedance. And since it basically depends on L and C, which are characteristics of the transmission line, right? This is called the characteristic impedance. And often abbreviated by, is often called Z naught. So, therefore, if we have the voltage, which is F1 of x minus Ct plus F2 of x plus Ct, then the current I of x comma t is basically F1 of x minus Ct by Z naught. What comment can we make about the current corresponding to F2 of x plus Ct? Minus F2 of x plus Ct over Z. Alright. So, fortunately, it turns out that there is a nice way of interpreting these results. What this math is telling us is that now basically this is the symbol for a transmission line. At any point x along the transmission line, the voltage can be represented as the sum of two quantities, F1 of x minus Ct and F2 of x plus Ct. So, let us try and take a look at what this F1 of x minus Ct actually means. So, let us say F1 as a function of its argument is some function like this. Alright. So, in other words, let us say if I took a snapshot, if I took a photograph of the voltage on the line, if that was possible, with at t equal to 0, what would you get? You would get F1 of x, right. And what have I done to get F1 of x? At t equal to 0, right, I had an imaginary camera which would basically capture the voltage at all positions along the transmission line and then give me a picture, right. Now, at t equal to t1, what do you think how will the picture look like? I do the same thing again. Well, all that it says is this is going to be F1 of x minus C times t1. So, it is going to be this is C times t. Alright. So, at t2 greater than t1, how will this look like? the shape will look the same, except that how much would it have traveled? Yeah, this will go, this is f1 of x minus ct. Right. So, the interpretation of f1 of x minus ct is simply a wave traveling in the forward direction, right, and likewise this is a voltage wave traveling in the backward direction, right. So, this is the forward wave, this is the backward wave, correct. And corresponding to the forward voltage wave, we also have what does that represent? We have a forward current wave, which is simply the voltage wave divided by an impedance, right, and the forward wave is going this way, the reverse wave or the backward wave is going that way. So, it stands to reason that the current that corresponds to the backward travelling wave is going in which direction? It is going in the, yes, it is going in the opposite direction, alright. Okay. So, basically this is the backward current wave. So, at any point on the transmission line, you can write the voltage waveform as a sum of the voltage and the forward and the backward travelling voltage waves, and the current at that point is basically the difference between the forward and backward travelling waves, okay. And the amplitude of the current wave is simply 1 over z0 times, which is simply the amplitude of the forward going voltage wave divided by the characteristic impedance, and likewise for the backward, right, okay. And this is all you need to understand distributed circuits, at least for a whole for a good first level understanding of distributed circuits, okay. The rest of it is just simply a derivative of, just simply applying these laws to, this is another circuit element, that is all, right, and then now you just do circuit analysis with this new element in place. So, let us kind of build on what we have learned so far. So, let us say we have a transmission line, right, which extends to infinity. So, at some point x, let us say at x equal to 0, we have a forward going wave and a backward going wave, okay. V plus with a superscript plus is often used to denote the forward going wave, and V minus is used to denote the backward going wave, right. And so, what comment can we make? Remember, this line goes to infinity, we do not know where it goes. So, at a distance say x to the right, what comment can we make about the forward going wave at position x? Or rather, if you knew that the voltage here was V of x comma t, what comment can we make about the voltage there? about, let's call this, sorry, V plus of x comma t, right. What comment can we make about the voltage waveform at place x, the forward going voltage wave at x? Sorry, this is V of 0 comma t, yeah. This is V plus of x comma t, right. How is V plus of x comma t related to V plus of 0 comma t? Exactly, right. So, remember, this forward going wave is traveling in the positive x direction with a speed c, correct. So, whatever happens at position x equal to 0 will happen at x at a time x by c later, right, because it's going this way, right. So, basically V plus of x comma t is simply V plus of 0 comma t minus some td, where td is nothing but x over the velocity of light. Likewise, if this is v of 0 comma t and this is v minus of x comma t, what comment can we make about the relationship between these two guys? V plus of v minus of x comma t is, all that this is saying is that the backward going wave at 0 is delayed with respect to the backward wave at x. Does it make sense, people? Right? In the Laplace domain, V plus, if we call this V plus, and we call the voltage here V minus, what would be the Laplace transform of the forward going wave at x? This would be V plus delayed by td, so it would be e to the power minus s times, and likewise this would be V minus e to the plus s times t. Is it clear, people? Very nice. Now, what comment can we make about I plus, the forward current wave at this point at x equal to 0? We know the forward voltage wave. So, what is the forward current wave? Oh, well, the current here is V plus, the forward current is V plus over Z naught. The backward current is, the forward current, is this, the backward current going in that direction is, since the direction is already there, it is simply V minus by Z naught, alright. And what can we say about the forward current here? It is simply V plus over Z naught e to the minus s times td, and likewise this is V minus over Z naught e to the s times t. Correct? Does it make sense, people? Have you guys seen all this? You must have seen all this before, right? Yes? Now, all of you might remember these bounce diagrams where you cannot draw the pictures of waves bouncing around and so on, right? It's all pretty straightforward stuff. It is meant as a refresher. Okay, all right. So now let's see, what happens to a short circuit. Well, let's say, remember we were trying to measure our y parameters, and we connect, this is, we can only short the ends of some conductor of some finite length, right. So let's call the length, though we know that it's going to be physically long, we are going to call the delay. So, we are going to denote the transmission line by two parameters. One is the characteristic impedance, right, and the next thing we need to know is how long it is, right. How long basically does not really matter as much, it is more how long the wave takes to go from point A to point B, correct. So, it is basically the length of the line divided by the velocity along the line is basically the delay of the line. So, we will simply characterize the line by two parameters. One is the impedance, the other one is the characteristic impedance, the other is the delay. Does that make sense? Okay, all right. So, now let us try and see, we have a transmission line with this characteristic impedance and delay. I shot the other end of the line, right. What would be the impedance looking in here? Correct. So, what do we do? I mean, if you want to find impedance, what do we know? I mean, what do we do normally? You apply a voltage, measure the current, or vice versa, right? So, we need to figure out, how the voltage here is related to the voltage at this end, on the left end is related to the voltage at the current, how the voltage at the left end is related to the current at the left end. So, what do we do? Well, we know for sure that